Hello and welcome. Today I'm going to talk about a simple aggregation rule for penalized regression coefficients after multiple imputation. My name is Ryan Peterson. I'm an assistant professor of biostats and informatics at CU. So as a motivating example behind the talk and a true story, early here in Colorado during the pandemic, researchers wanted to fit a sparse predictive model to intubation status for newly admitted patients. The aim being for decision-making processes, it would be helpful to be able to say who's at high risk and who's at low risk based on a few participant characteristics. Now, primarily these were going to be applied by non-statisticians. Unfortunately, though, when I got the data, I saw that the training data had considerable missingness, which complicated the modeling of it. So how do we build an interpretable predictive model in the presence of substantively missing covariate and outcome data? Now, we weren't the only ones to come across this problem. Others had dealt with it using single imputation, and others had done complete case analysis. I'll touch on those in a minute. But in a recent systematic review, it's actually been shown that a lot of these predictive models for COVID-19 that have been developed, almost all of them have various flaws and biases, in many cases stemming from the improper treatment of missing data. So to outline the talk, as I said, I'll go through a little bit of background on missing data handling and model selection methods. More importantly, though, how to combine those two together in a way that makes sense. So we talk about a couple of the ad hoc methods you might consider, and the one we ended up going with, which is the Malcolm method. And there's also a few alternative methods that we looked at after the fact. Most importantly, which model worked the best. We'll provide some recommendations and do a predictive model bake-off, as well as a simulation study. So you're probably familiar with the complete case analysis approach, aka listwise deletion. So if you can assume that your data are missing completely at random, aka there is a monkey who's throwing darts and randomly setting values to missing in your data set, then you can use listwise deletion and still expect to see unbiased estimates. However, there are still downsides. So in the hypothetical example here on the right, you can see we've got an outcome and 3 covariates with a spattering of missingness here. Even though only 28% of the data are missing, we'd have to delete all of the rows which don't have complete data. So all but rows 2 and 8 would have to be deleted. And this throws out a lot of data. It does make your models more unstable and less precise as a result. So overall, complete case analysis isn't great, especially when you're doing something like building a model and doing model selection. A single imputation analysis is a little better. It's going to be unbiased when you have data that's just missing at random. In other words, data that has missingness dependent on other of the observed data. With a single imputation analysis, we get to use all of the observed data. We kind of fill in the missing pieces in red here, and assume that we kind of know those, even though we don't. This was taken by a couple of the other papers, including Gong et al., that did a COVID model. So the benefits of this is that it throws out no data, but it can make your models actually too precise, and that actually makes them unstable as well. So it's not ideal necessarily to do the single imputation analysis approach. So the best way, in my opinion, is this multiple imputation approach, which proceeds in the figure as in the figure on the right. So you start by doing that imputation approach, but doing it multiple times. So in this case, we do it 3 times. We're going to run the analysis on each of those as if we did have the complete data. And then at the end, these analysis results will all be a little bit different depending on the imputation procedure. So you're going to pool those results at the end using some kind of rule to do that. And the benefits of the multiple imputation approach is that you have unbiasedness under MAR data, and the standard errors of your final results will be correct. It won't be too precise. In other words. So this is a pretty popular approach for that reason. There are other methods I'm not going to get into, but I'm happy to chat about why in the live session. So which of these methods was best for our COVID data? The multiple imputation method was best for our COVID data. We didn't want to throw out a whole bunch of data, and there were pretty distinct patterns in the missingness in the data that we could detect and control for with an imputation procedure. So yes, we went with the multiple imputation procedure. Now for model selection, there was a lot of correlation among the predictor variables, and for a variety of reasons we wanted a parsimonious model, both practical and statistical reasons. So our options in this regard, we could use a best subset selection or a stepwise selection procedure. We also wanted to look at regularization procedures like lasso, ridge, and elastic net, and non-convex regularization as well. So for instance, the minimax concave penalty, which I'll refer to as MCP. Ultimately, we landed on the last of those, non-convex regularization procedures, because of these reasons listed here. It's easy to tune, computationally efficient, which is important with a lot of data sets or a lot of imputed data sets. It doesn't yield biased regression coefficients, and it tends to arrive at a sparser model, or more parsimonious model than the lasso or the elastic net procedures. Okay, so we decided on MCP, we decided on multiple imputation. Now, importantly, how do you aggregate your coefficients after performing MCP on each imputed data set? So we're left with this matrix of m by p parameters, and the entries for this, in terms of columns, the j columns are going to either be 0 or some number on the real line. That's not 0 if the variable was found to be active in that particular imputation. And how do you aggregate a variable that's this kind of weird looking variable? Do you use the mean, which would be the case if you were to use like Rubin's rules? Would you use the mode, which would almost always be 0 because if the variable is not selected, it's discrete. If it is selected, it's not. Or do you use the median? Well, the median here has the nice principle that at least half of the imputed analyses actually have to select that variable in the same direction in order for that to be pulled into the aggregated active variable set. So we went with the median, and we put a fancy acronym on it called the Malcolm approach. Here is what Malcolm stands for, and while I did get a little bit of resistance from a reviewer on the quality of that acronym, it was the best I could come up with, and it's very easy to say. So I went with it. An alternative approach is the MI lasso. So this was developed as a solution to the multiple imputation problem, aggregation problem in the lasso setting. And it's actually pretty clever. Rather than distinctly performing model selection for each imputed data set, the MI lasso jointly models all of the imputed data and uses the group lasso such that if a covariate is selected in one imputation, it has to be turned on in every other imputation. So in addition to that as a strength, the MI lasso does have software available to fit and tune those models using BIC in the Gaussian setting. However, it's limited, currently anyway, in that it can't do non-convex regularization, and it's pretty difficult to do anything in the non-Gaussian setting, as well as do cross-validation. Okay, so that said, we can still do a comparison of the MI lasso approach to our method in our application. The only difference is that we're going to have a linear probability model for that aggregated MI lasso procedure. And the model that is arrived at, if you do that, is listed here, where we have a baseline probability of 39% that someone gets intubated who comes into the hospital with COVID-19. And then that gets modified by their CRP value, z-score, their LDH and NLR z-scores, as well as their diabetes status. So in the case of MCP, though, we fit binomial family logit link models, so the coefficients are on the log odd scale and they can't directly be compared to these. We can, however, see the imputation-specific results for the MCP approach as well as the Malcolm approach on the bottom here that aggregates all of the imputation-specific procedures. And we see the Malcolm MCP approach arrives at the exact same selection as the MI lasso approach did, which is good. But you may be wondering, okay, they are slightly different models, so how well do they compare to one another in this application? So researchers did care about predictive accuracy, and so they actually collected data prospectively on 102 new patients to see how well their predictive model performed. So they did this, and after the fact, I then compared how well our Malcolm MCP approach compared to the MI lasso on this prospective cohort after having trained the model on the initial data set. And you can see here, the bottom line is, it really didn't matter which method was used. All of the methods performed about the same. And, this was somewhat unsatisfying because it's a kind of a null result, but it still made us all feel better about going with the Malcolm MCP approach in the original manuscript, because if we had gone through the process of creating or doing the slightly more difficult MI lasso procedure, it wouldn't have changed our results all that much. However, if we want a more powerful comparison between MI lasso and the Malcolm methods, we can do so in a simulation. So we did that. We performed a simulation where we kept it, for the most part, looking like the data at hand, but we did vary the percent of data that's missing as well as the signal-to-noise ratio. And this is just a subset of the simulations we actually did. So looking at the predictive accuracy results for this, you can see that for AUC, the Malcolm-Lasso, Malcolm-Elastic-Net, and MI-Lasso all yield models which predict similarly well in the low signal-to-noise ratio case, which is up here. Malcolm-MCP didn't actually do that well in that case, but it's actually well known that MCP is going to do better in high signal-to-noise ratios. So if you look at the bottom with a high signal-to-noise ratio, you can see the opposite pattern. So the Malcolm-MCP approach actually does the best of any of the Lasso or Elastic-Net-based procedures. And if you pair that with Malcolm, you can kind of reap the benefits of the improvement in performance that you get with MCP. So finally, some discussions. I do think it's worth noting that sometimes ad hoc approaches do work and are warranted, the Malcolm method being an example of that. So despite its simplicity, Malcolm methods do competitively to other methods in terms of predictive accuracy and selection performance. And I really think its main benefit is its versatility. So in settings where MCP will perform best, MCP can be paired with Malcolm. Settings where Elastic-Net will perform best, Elastic-Net can be paired with Malcolm, and so on and so forth. This is true for any kind of model selection procedure, really. So single imputation procedures we've also found to be unstable. So on that table here, you can see that the Malcolm model, after aggregation, that was actually only selected in 35% of the single imputation procedures, meaning that if you, for instance, only did a single imputation, you might be in this case of imputation 5, where you have a really overspecified model. And so really to benefit from that aggregation and the multiple imputation, the Malcolm procedure does do a pretty good job of doing that and increasing the stability of your model selection procedure. All right, a quick addendum here. I do enjoy software development and pairing new methods with new software packages to aid in their implementation, but I was still pretty excited to publish a paper for which the only software required of the suggested method is the median function. I thought that was kind of nice for a change. I do want to acknowledge Drs. Erlingson, Winham, and Hirsch, who really helped direct this problem, as well as the many students who helped with the data collection and the Center for Innovative Design and Analysis that I work with. Here are the references I mentioned, and thank you all for listening. I hope to see you at the live session to answer any questions that you have. Thanks.